That's the obnoxious part about that. I know. I should really just put my phone in airplane mode.
Is there any way to write S? Something?
S? You can just say this.
Right.
All possible sets, 5 cards, whatever. Just make it very clear that you know what we're talking about. So that was just to make sure that you understood what exactly I was saying. That's why I wrote twice. And then, but here's the important note. Size of S. It's how many 5-element subsets you can get from a 52-element set. 52 choose 5. And the probability of each one of those then is just 1 over 52 choose 5. Pretty small. They're all equally likely. Yes, a particular poker hand has a very small probability of getting it. So the odds of you getting those exact cards is very small. All right, let's do another one. Let's say that we were talking about tossing a coin 5 times. Our sample space then could be all the possible outcomes. We could have gotten heads, 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 or heads, 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 tails, or all the way down to tails, 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 tails. Okay? What's the size of S? We had 2 options for that one, 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 2 options for that one. 2 to the 5 is 32. Chances are what I wrote up there is right. Probably. Or maybe I was just trying to trick you. Now, be careful, because what this is saying then is that heads, 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 heads is just as likely as heads, tails, tails. These two are the same likely?
Yeah.
Yeah, okay. Good, don't fall in that stupid pit. Okay. There was a teacher who, he told his students that he wanted them to go home and flip a coin 100 times. Or they could just write down 100 coin flips without actually doing it and show him the string that they end up with. And he could tell them whether or not they actually did the experiment.
Right, yeah.
And the way that he could tell whether or not they actually did the experiment is if you actually do that, then there's a pretty good chance that you'll get a long string of heads somewhere in there, or a long string of tails somewhere in there. But if you're the person randomly doing it, you're never going to put a long string of heads or tails in there. So that's all he would do. He would look for a long string of heads or tails. I think the magic number was like 7 that was going to come up. And so if they never put that in there, odds are they didn't do the experiment. So we have a tendency to think just because a lot of heads has come, that means a tail should come next. No, it has no effect.
Yeah.
The coin doesn't remember what it did.
Right.
It's one of the big problems with how roulette makes all its money. People think, oh, a lot of blacks came up. Good chance of it being the heads. Because when it's all said and done, half of them should have been red and half of them should have been black, right?
Right.
So if a lot of blacks came and in the end it should even out, a lot of reds are on their way. Right?
Well, that is true. That makes perfect sense. Alright.
Only over the course of a large amount, though, right?
It's the difference between conditional probability and non-conditional probability. The odds of me rolling a 6 right now are a lot different than the odds of me having rolled a 6. Once the outcome's over, it's different probabilities.
Right.
So once a few of them have already been determined, it changes the probabilities.
Maybe it's conditional. Right?
Well, they're saying overall half should be black and half should be red. Okay, let's say you just barely got 10 blacks. Now overall half of them should not be red and half of the remaining should be red and black.
Okay, so
Not
my
half should
question.
be overall.
So if you roll the dice 5 times, and you get 1 through 5, your 6th roll, what's the probability of you getting 6?
The same as it was before you started the
1/6?
experiment.
Okay.
Yes.
I know.
Good.
Alright.
All right. So that one makes good sense. All right, let's look at another one. Here, you don't know what the real world phenomenon is. I'm just giving you a sample space, right? So I say S is 1 through 6, whatever that represents. And I give you my probability function. I say 1 is 0.1, 2 is 0.4, 3 is 0.1, 4 is 0, 5 is 0.2, 6 is 0.3. Is this a sample space?
Yeah.
Second section, events.
Can we go all five sections?
Today?
That's what it says.
5?
5 sections. That's what it says, right?
Where is you? Right here.
No, look on the.
Oh, yeah. Oh,
Section 30,
We're good.
32.
Yeah.
Did we just finish 30 already?
yeah, that's it.
Wait, that's what we have to do.
That was funny.
Yeah, let's move on to 31.
Yeah.
Events. Okay. An event is, well, let's just read the definition exactly. So once I have the sample space defined, event doesn't make sense independent of the sample space. Once you have the sample space. So let SP be some sample space. An event A is a subset of S. Okay? Just get down exactly what the definition is. An event is just a subset of whatever that set is right there. Okay? The probability of an event A, which we denote P of A, is the probability of each of the elements in A.
What
Okay.
does that mean?
Alright, let's see an example, then go back over the definition. So, let SP be the sample space for rolling a pair of dice. What I meant by that is let it be the same sample space that we used here. Okay? So, let SP be the sample space. Oops, this one. For rolling a pair of dice. And let A be the event of rolling a 7. In other words, A is 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1. Those are all the rules that give you a 7.
Okay.
So far, is A a subset of S?
Yeah.
Yeah. S is all the possible ordered pairs between those elements. Now, A is a subset of S, so it's an event. What's the probability of A? It's the sum of the probabilities of all of its events.
Okay.
Or sorry, of everything in it's an event.
Right.
It's the probability of each of its outcomes. It's the probability of the 1, 6 being rolled, plus the probability of the 2, 5, plus the probability of 3, 4, plus 4, 3, plus 5, 2, plus 6, 1. Each one of these probabilities was 1/36. There were 6 of them, so its probability is 6 out of 36.
You can just look at A and see what the probability is of each one, right? Because
That's what we did.
I'm saying without fussing it up, because that's kind of what I heard you say up there.
Yeah, so
It's still 1, 6.
So here's the fast way you do it now. You say A has 6 elements. Each of them has a probability of 1/6. Therefore, A has a probability of 6/36 or 1/6. I just wrote that out so that you would understand explicitly what this notation was saying.
Is there a faster way to find A, or do you just have to go through and find out the possibility?
You'll, as for particular events, you'll come up with tips, ways of thinking about it that make it quicker. It's just like, I mean, really, we're going to get back into counting. Counting and probabilities are very related. Obviously, what did we do? We counted the size of A and then multiplied it by the probability of each event. So it's just a matter of, can you count with a clever way to count? It's like we came up with a clever way to count this. Are there other ways you could have gotten this? Yeah, this is just an easy way to count it.
Yeah, I guess that's true.
So it's just like how we've been counting. There's no, this is the way that you count it. It's count it however you can count it, whichever way makes sense to you. And what it is what it is. Okay, so let's do an example that's not so trivial. So let SP be the sample space for tossing a coin 5 times, meaning let it be the same sample space we developed here. And let A be the event for flipping a heads once. When I say once, I mean only once. Not at least once, but only once. So you only flipped heads once. And B be the event for flipping heads twice. Okay? So now what's the size of event A? How many of those outcomes have a heads only once?
5.
5?
Hang on.
Because you could have heads, tails, 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 or you could have tails, heads, tails, 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 or you could have tails, tails,
Oh,
heads,
yeah.
tails.
Yeah, right, that's right.
Yeah, perfect. you can have the heads there, or there, or there, or there, or there, and the rest have to be tails. There's 5 of them. So, there's 5 of those that have only 1 head. So what's the probability of only getting 1 head? 5 30 seconds. Or 5 over 32. 5 32s
Makes perfect sense. Yes.
is 1 per 60.
Okay.
Alright, B. The event for heads twice. Ah, who can calculate this one?
2.5.
2.5. That's probability can't be more than 1, so there's a hint. And I'll give you another hint. The probability is not 1. It's less than 1. No, you hype up. Get on my level. Don't drive me down.
We know how to do this. Why can't I
I
remember?
don't know.
Well, you better figure it out. There's a blank spot on the whiteboard. You want the notes to be complete?
Is it 5 choose 2?
Why would it be 5 choose 2?
I don't know.
Oh, it is
Right.
5 choose 2.
It's not.
It is 5 choose 2.
Okay, why?
Because
There's 5 possibilities.
Right,
There's-
yeah, okay.
there's 5 locations. You choose 2 of them to stick a head.
Right.
So you think about it as your set is 1, 2, 3, 4, 5. And now you're going to choose 2 of those to put a heads in. So you might choose 1, 3. Well, that corresponds to the choice of heads, tails, tails. So yeah, the answer is 5 choose 3, or choose 2. And what is 5 choose 2? 10. So this is 10. So this is 5/16.
All right.
10, 30 seconds.
Right.
Just, I times
Right.
that by 2. Was my thinking. Alright, let's play again. Okay, now you have 10 fair dice, 10 fair 6-sided dice. I didn't specify 6-sided, but 10 fair 6-sided dice. You roll them all. What is the probability that you do not roll a 1? First off, let's talk about our set of outcomes. S is going to be the set of all these 10 tuples, where each one of these represents the outcome of a particular die, right?
Yeah.
So we have 6 options for that, 6 options for that, 6, 6, 6, 6, 6, 6, 6, so 6 to 10.
Oh, so
That's the size of S.
is that including 1?
Yes.
No, this is S. We haven't talked about the event A yet.
Yeah.
Oh, that's the event.
So that's
So-
including 1.
That's the set of all possible events, that's S. I'm just creating our sample space.
Oh, okay.
Here's S. What is our probability
5 to the
function?
power of 10.
1,
I got it.
hold on.
How is that not right? Just means right.
Our probability function assigns the same probability to each outcome, right?
Right.
So now how big is A? Our event of not rolling a 1. And Estonia says 5 to the 10. Hopefully someone can correct that.
That's wrong. Dang it. 6 to the 9. Because there's 6 ones.
It's 5 to 10.
Woo!
Just want to see if someone comes something different. So yeah, it's 5 to the 10. We don't roll 1 there, we don't roll 1 there, we don't roll 1 there, so 5
So
options 10 times.
Yeah.
And what's the probability?
1 over 5.
5 to the 10 times 1 over 6 to the 10, or a lot of different ways you can write that. But that's the probability, right? Okay. Now I'm going to give you a problem that I just like to give. It's not a book. Now that you guys have all this background for probabilities. I have a 6-sided die. Here's the game. You choose a number between 1 and 6, and I give you 3 tries to roll that number.
What's the probability that you're right?
Yeah, what's the probability that you roll the number? So we play a game, it's a betting game. you have to pay me $1 to play. You pay me $1 and you pick up a 6-sided dice, you pick a number.
Will you write that down? Yeah.
Then let's pick a particular one. So let's say I'm playing the game and I'm going to try and roll a 3. So, given a 6-sided die, what are the odds of rolling a 3, some number, at least once in 3 tries? So I give you the die. You have 3 chances to try and roll a 3. What's the odds that you're able to do it? There is a 1 in 216 chance of you doing it. You have 3 tries.
Hang on.
In your first try, there's a 1 in 6 chance, so it can't get worse.
You're right.
You're saying like that's almost impossible. Isn't that a pretty fair game? The game should be fair, shouldn't it?
No.
It's a 6-sided die. You get 3 chances to try and roll the number.
You get 1/6 3 times, right? So it's 1 in 18.
How is your probability getting worse?
I don't
Would it be
know.
one?
Hang on.
I don't
It's
know.
1/6.
1/2 is the intuitive answer. It's wrong, but it's intuitive. So no, it's not 1/2.
And I'm totally
But most people
wrong.
would say 1/2. You're pulling out answers I've never heard someone give to this.
Sorry. I know they're wrong. It's totally wrong. I'll try it. It'd be
Give you a hint.
1/3.
The answer is more than 1/6. Our answer is more than 1/6. So it turns out getting more than one roll helps.
Oh, thank you for that. You did that.
And no, it's not 1/3. So the event is rolling a 3 at least once. There's a reason that I waited until we did the previous
1/6
process.
to the 3. Now we gotta figure out what are the odds of rolling 3.
Oh, you're saying the probability function
Then
is.
yes.
Okay.
And now that, what are the odds of rolling 3? 3. So then it's 3 over.
If it's 6, it
It's
seems
not
like it
3.
should be a half because
Which
if
is
you have
then
3 tries with
So
6.
you're saying it's 3 over 216? Is that 6 to the 3, 216? 6 to the 3 is a big number, right?
Hang on.
36 times 6. What is that?
Okay, hang on. Oh, so it's 3. Okay, so you have 3 chances to get a 3.
216, yeah, I got that right.
Oh, so it's 1/2.
Yeah, well, we thought it was 1/2, but it's
Not
not
yet.
1/2.
1/2 over 6 to the 3.
1/2 over 6 to the 3 is way less than 1/6. I'm telling you it's more than 1/6. 0.5 divided by 216.
Oh. Wait, 1/2.
0.5.
What the heck?
Is it not? No.
Okay, it's legit 6 to the 3. I'm sorry.
It's not.
6 to the 3?
Yes.
That's greater than 1.
No, it's not.
6 to the 3 is 216.
0.316.
I was just randomly creating.
Okay, will you just tell me the answer?
No,
I don't
I
like
want
it
to
anymore.
no.
Next thing I'll say is, If you can't figure it out that way, think about the odds of losing instead of the odds of winning.
Okay. Oh, okay, that makes more sense, I guess.
Two to the 3 over 6 to the 3.
2 to the 3 over 6 to the 3. No, that's a small number, but
How?
well,
That's
is
1/3.
8 over. That's not 1/3. That's 8 over 216,
God.
which is a lot less than 1/6. This is a question I use when someone says that they know probabilities. This is actually a real simple question.
I know it is. I don't even get it. I'm trying.
Okay, what are the odds of losing?
All 3 times.
Yeah.
Well, your samples, the size of S in your sample space would be 3, 6 to the 3, right?
Okay.
And then, so your probability of any one of those events is 1 over 6 to the 3.
Right.
And then you have to,
Right, and then what's the size of A? You take it away, right?
How
It's just
many
like
A's
none of
don't
them
have
are
a
one.
3?
None of them
So
are
it's-
A is none or 3.
So then it's
so it's
2 to
5/6 to the power of 3.
There you go. Right? So if we're doing odds of losing, then A is, the size of A is 5 to the 3. These are all the rules that don't have
I know!
the size of
It was
S
6 to the 3.
is 6 to the 3.
Why was I saying
So
2?
the odds of losing, the probability of losing is 5 over 6 to the 3.
So the probability of winning is 1 over 6 to the 3.
Okay. Wow.
That's wrong. Sorry.
So what are the odds of winning now?
This is the same thing, isn't it?
No.
It's not 5.
If this came out to 99%, would the odds of losing also be, or the odds of winning also be?
So it's, why? I feel like 1 over that? I don't know. That's not right. That's not right at all.
Ah, wow. Okay, you guys didn't have a chance to begin with. This was the lead.
Sorry.
That is what I was doing in my head.
So that's the probability of losing.
Except I was.
So what's the probability of winning? You guys are killing me.
1 second.
If the odds of losing a game are 60%, what's the odds of winning the game?
I feel like it should be 40%.
40%. How did you get that? Did you just do 1 minus the odds? So 1 minus 5 over 6 to the 3?
Wow.
So if this is your odds of losing, these are your odds of winning. Crazy. Which is equal to, let's see, that's going to be 1 minus 125 over 216. So that's going to be 216 minus 125 over 216. What is that? Is it 91? 91 over 216. Right? Which, as a probability, what's that going to be? 0.4 something. 0.4 something. So 40-something% would be your odds of winning. So if you were to play that game, you'd lose money. In case you ever want to scam some people. Let's see what it is. 42%. So it's close enough to 50% that if they played it, they probably think it's fair. They'll play enough times and they'll rack up some money.
Yeah, they can still lose money over the course of the day.
Yeah. So what's the odds of them losing?
Well,
Roughly 58%, right? Okay. Just making sure we remember how to do that.
can we do another one so that I can try again on something like that? I can even practice.
Here's a real simple one that people screw up all the time. I don't know if I've already told you guys this one. Jack and Jill have 2 kids. One of them is a boy. What's the odds that the other one is a boy?
50%.
No. What? Jack and Jill have 2 kids. One of them is a boy. What's the odds that the other one is a boy?
That they're both boys? Is that what you're saying?
25%.
I don't even care anymore. If you would think about it, you could get it.
It's
Oh,
not
we
50%.
didn't talk about it.
Jack and Jill have 2 kids. One of them is a boy. What are the odds that the other one is a boy?
0%.
That,
There's no chance.
People have 2 boys all the time. Jack and Jill have
2 kids.
100%.
One of them is a boy.
Okay.
What are the
Oh,
odds that the other
0%.
child is a boy?
100%.
Okay, it's not 100%, it's not 0%. Let's rule those out.
75.
No.
Obviously, the male gene is
All
dominant
right.
in that family, so.
Yeah. S is, let's see, what are all the possibilities? They could have boy boy. They could have boy girl.
That's it.
They could have girl boy. They could have girl girl.
Okay. But
Wait, can they have girl girl?
No.
No, because one of them's a boy.
I
Okay.
said 75.
What are the odds that the other one is a boy?
The 133, I guess.
Almost. Your thinking's right, your answer's wrong.
Okay.
33%. 1 in 3. You said 1 in
Oh,
30.
sorry, that's what I meant. That's
Yeah,
what I
I know.
meant.
Wait, 1 in 3?
Yeah.
Oh.
One of them's a boy. What's the odds that the other one's a boy, or that they're both boys?
Right. That makes
Could
perfect
be any
sense.
one of those. Okay. So,
Not hard,
You see
right?
where I got 25% though?
yeah, no. Yes? Yeah, I guess.
You do though.
The
2,
I
oh,
did
oh
the
yeah,
exact
because
same thing,
you were
only I
doing
left the
this.
girl there.
Right.
Right. 6, 6,
Like
7,
text
6.
Right, so that would be the answer to the question. Jack and Jill have 2 kids. What are the odds that they're both boys? Then 25% would be right.
Okay, yeah, that makes sense.
I've all.
Yeah, people are terrible at
I
probability.
just thought probability. Like in all my past years.
I love probability. I love it.
It's fantastic. Actuarial maths are
It's fun.
a ton of fun.
Is that all we have to do today?
No, I didn't finish the section. We already covered what we had to do today, so we're on track.
So,
We're on.
what's the whole?
I don't know why I only assigned 1 section for all that.
Because you wouldn't get it.
Maybe because I spent a lot more time last time hammering home the idea that
Yeah, we're smarter than the last class.
hit and miss.
Savage.
Well, how many kids do you have?
You're working better than they did. But
Our intelligence.
you guys were more like right here, whereas they were more like this. You guys were more steady.
What? That's wonderful.
Like I had more people that would be able to answer my questions, but I also had more people that I had to work with forever to get them to up. With you guys, I don't have to work that hard to get everyone at the same level, but no one's getting the answers.
So it's more like the line was like this and we're right here.
How big was your last class?
I'm terrible at remembering stuff like that.
It's last year.
I'm terrible at remembering stuff like that. Like I could give you an answer, but could be off by as much as 6 students. My gut says like 11. I wouldn't be surprised to find out like 5. I have to think about the students. I have James, Mim, Roberta.
Yeah, Brooke and Taylor, right?
I had Taylor,
Miranda.
not Brooke. I had Miranda. I had Megan. I had, oh, what's the dog student kid?
Marcus.
Jeremy. I had Byron.
Yeah.
I think that's his name.
Was he last? You last year?
Yeah, he seemed to put him in the
Yeah, he wasn't there all the way through. I had, oh, Clark. Clark.
So was that 8? Is that where we were at?
No, that's 11.
I don't know where I'm at.
All right.
I don't know. Hard to remember stuff like that for me. I definitely won't remember I taught you guys.
Okay. So,
I think this is your favorite class, to be honest.
My favorite class? You're saying group of student-wise or
Yeah.
teaching discrete math?
Yeah.
My favorite class by so far has still been my first physics class.
did you teach?
That was
Did you teach
unlikely super class. My worst student in the class was your big brother Patrick, and he was not a bad student.
He's a great student.
He's a great student, and he was the worst student in the class.
That's
So
wow.
that was a unusually high performing class, which is good because my first time teaching physics, I was not ready to teach physics. It's not even want to get my degree in. I had done physics and then now I'm teaching physics. It's like you guys teaching this class when you finish here.
Oh, yikes.
Yeah, exactly.
Not be able to
Yo,
teach it.
that'd be insane.
It's
The
not
kids
what I was
will
getting my
question it and they go,
education
"I
in.
don't
So
Johnny.
I kind of lucked out. I had such a high
You're at
performing
the
class.
end.
Yeah. Yeah, I had my brother Matthew in it, Mark in it, Patrick in it.
It's only been like 4 years or something.
Oh, probably more than that. That was my first year teaching.
Oh, it would have been 5 years
So
ago.
that was my first year off my mission.
Patrick's 5 years old.
So probably 5 years ago. Sound about right. Yep. Crazy, crazy.
Or I guess 6.
Or 4. Were they, no. Were you, wait, were they seniors or what?
Would have been 2 years.
I think Matthew and Patrick were seniors and Mark was a junior. Mark wasn't in that class. For the next year. So, 2 seniors and a junior? No, I had another senior in there. Who wasn't? Alright. But yeah, unusually high performing class, so. And physics is just so much fun to teach. I need to take it back.
Well, it's not during this period, so
Yeah,
you could change that up to tomorrow morning.
I need to take it back. That is it.
I would have taken it.
There's so many misconceptions about physics. Like what I do with you guys with probabilities.
If you were to teach,
I could do that with the physical world over and over again so many times. I mean, you completely misinterpret the world around you. It's amazing how many misconceptions you have about the universe, which is just really common stuff.
sure.
And even stuff, it's kind of just, some of them you can like laugh out. Most high school students, I don't know why this is understood, but what causes the seasons?
The tilt of the earth.
Oh, got it.
What did you think?
The vast majority of people say the earth gets closer to the sun and further away from the sun.
That's not right.
And you can get them to say that, and then in the same sentence you can get them to say, if it's somewhere here, then on the opposite side of the world it's... So they'll have both those ideas, and I can get them to say both those things in a conversation, and no conflict occurs in their brain. It is great. And so little things like that, you can get so many of them. Just every section, you can bring up a different one. So I had, the way you got extra credit in my class there was, come to class with a misconception, common misconception. Very sensible. Then we go over whatever it is at the beginning of class, just answering weird questions, you know. Like microwaves causing cancer.
That's awesome.
It
That's
is.
pretty much what we do in
Physics is a
chemistry.
physics is a ton of fun.
I'm sure it's what we can do in that too.
Chemistry is another great one for doing that because chemistry is so easy that there's so much extra time to it.
Yeah.
It's so easy.
Well, when I say it's so easy, I should probably qualify that statement. I'm thinking compared to physics. Physics, the math is intense. The math in chemistry is so far from intense. It's ratios. That's the math in chemistry.
It's pretty easy.
In physics, every chapter you're developing a new mathematical model for the physical phenomena that you're dealing with. And so all the hardest math that you do in chemistry, you do as one of your chapters in physics. So it's a mathematically intense class. You have to learn a lot of math that you can't just do ratios. But chemistry, since the math is easy, you have so much time to just talk about the ideas, and it's easy to wrap your head around it, just start solving problems with it. Whereas physics, I was always on the crunch just to get through the example problems before the end of class because
It's hard.
yeah, because the math is so different every time, and you have to come up with different ways of thinking about stuff. It's just, well, it's a great class. I'd love to teach it again.
Probably teach next year if we talk it over with someone.
That's the problem is more and more you guys don't have the math prerequisite for that class. Like the way he's teaching physics now, when I was talking to him, obviously I'm not positive what he's doing, but he was just giving me a high level view of how he's having to do it and the progress that we're making. The progress that we're making is exceptionally slow. And he's cutting every possible corner he can to dumb down the math. And to only handle like the simplest scenarios possible, which is really too bad. And part of it's because I don't know why the academy does not have that as a senior level class. Well, I do know why. I don't know why they would change it. Well, I do know why. It's bad reasons. It should be a senior level class. Trig should be a prerequisite class. And I would argue not only should they be in trig, but they should be concurrently taking calculus. That should be the requirements for medium physics. But out of my control.
Is it because you need calculus in physics or because the thinking that you have in calculus is useful in physics?
There's a reason that Isaac Newton invented calculus to do physics, because he had to. That's why. There's no way around it. And you severely limit yourself, you severely limit the problems that you can do when you don't know calculus. Now you can do that, especially before you get to electricity and magnetism. For early physics, it's doable, but for electricity and magnetism, it's possible. No, it's possible. So the book that they use is a trig-based physics. So it was designed specifically for the case where the student doesn't know calculus. And so what happens is the early physics dominates the book, and then later physics is way cut down. Whereas in the standard textbook, then it's 50/50. And so as it goes on, not using calculus is, it gets to a point where you can't keep going without introducing calculus, and then it's even kind of messy at times, hand wavy, how you have to make arguments because you can't use calculus, and there's sometimes that the author just flat out gave up and he says, this is a result of calculus, and just gives it to you. And then you use it because you gotta use it. It's a result of calculus. He couldn't come up with some way of like explaining it away to make it make some sort of sense. He just kind of throws in the towel a couple times and said, this is a result of calculus, sorry, we gotta use it, and then continue with the material.
Why, if it requires calculus so much, why do they make a junior class?
So here was the idea of Ariel Hammond when he came to the school. His idea was, junior year, you could take trig and trig-based physics concurrently. And then senior year, you can take calculus and real physics concurrently. Which, if you did both those things, oh my goodness, you would have such a great understanding of both mathematics and fundamental science. Like, that would be extraordinary if a student could get that and graduate. But that's never happened. So that's what he had in mind. So he pushed to have physics a junior level class that you can do concurrently with trig, specifically so that that could be an option for people. Now, I don't know, maybe there were some years where that happened, because I asked him about it, why he didn't. He explained that that was a dream, which is a lot of a dream. But if we're not going to do that, then physics should be a senior level class. And you should have as much math as possible before it, and then you enroll in calculus at the same time. Because that way, once you got far enough into calculus, you can start introducing calculus into your physics, which would be useful. Anyways, let's do another probability problem. 4 of a kind. We call it the poker hand sample space. This one. A poker hand is called a 4 of a kind if 4 of the 5 cards are the same value, e.g. they're all 7s or they're all kings. What is the probability that a poker hand is 4 of a kind? Alright, so let's calculate the probability of getting 4 of a kind. So we already know what the probability of a particular outcome is. So the question is, what's the size of A? How many hands have 4 of a kind?
13.
You're
Oh,
close.
wait, no, isn't that right?
You know, it's
Not
not answers, so
quite.
it's not them to say the same. Let's try again.
So we're talking about getting a hand where 1, 2, 3, 4. I probably should do it as a set because it doesn't matter the order.
No, 5.
5. A
Yeah.
poker hand. Oh, that's why you're confused. Okay. A poker hand is 5 cards. What are the odds that of those 5 cards, 4 are the same value?
Oh.
4 of them are 7s or 4 of them are kings. Does that make more sense now?
You were thinking how many different numbers could fit those positions.
So I deal you a poker hand. What are the odds that 4 of your cards are all 7s or all 8s or all 9s? 4 of your cards have the same value. What are the odds of that?
Wouldn't it be, well, you have 12 possibilities, no.
You have 13, and then you only have.
So
Oh, and then you have. So you have 13.
And then you have 12,
12, and then
12,
1, 1,
12.
1.
You have 13,
You only have
12,
1
12,
choice
12,
for the
12.
other ones. If it's right?
why do you have 12 for the second?
Because it can't be the same as first. Okay, or you could do 13.
So 13 is picking the value, right? There's 13 different values you can pick.
Right.
That's
Ace,
not
2,
right.
3, 4, 5, 6, 7, 8,
That's
9,
not
10,
right.
Jack, Queen, King.
I'm saying the first one is the odd one.
Well, do the odd one out last.
Yeah. So then.
So how many ways can we pick the value
13.
13? Once we pick the value, this has to be the same value, this has to be the same value, this has to be the same value.
Right.
Now what about this?
That's also
Well,
13.
No.
Because all 4 of them are used, so it has
4
to-
cards are used, so how many cards are left?
12. No, I'm saying because at 4 of the same number have been
48.
used, you can't use that number.
48!
It's not right.
It is right.
Oh, okay.
Pick whether it's going to be
I
ace, queen, king,
understand.
whatever.
I understand.
That takes care of those 4. Now there's 48 cards left to pick from.
Okay.
So 13 times 48. That was perfectly right. 13 times 48. And then so the probability of A is equal to 13 times 48 over 52 just 5. Right?
Okay.
Let's do another one. 4 children. A couple has 4 children. Which is more likely? They have 2 boys and 2 girls, or they have 3 of one gender and 1 of the other.
So we just have to find the probability of comparing.
Sure. So let's do. So first off, how many children do they have?
4.
So what's the size of S?
1, 2, 3, 4.
They have 1 child.
1, 2. Whatever.
So how many possible outcomes are there? They could have boy, 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 girl, boy.
Okay.
4 to the 4. 16.
4 to the
16, but not 4 to the 4. 2 to the 4, which is
2 to
16.
the 4. Not 4 to the 2.
Okay, so now let's say that A is they have 2 boys and 2 girls. Right? How many ways can you do that?
16 choose 2. No.
Sorry, what? What was the question?
So now we're saying that A is the event, 2 of them are boys and 2 of them are girls. What's the size of A?
Is it 4 choose 2?
Why?
Because there's 4 children and 2 of them.
There's 4 genders, choose 2 of them to be boy.
Yeah.
Yeah, 4 choose 2. So that's 4 choose 2, which is?
Can't remember.
4.
Oops.
3.
You did 5 choose 2, but you can't do 4 choose 2?
Can't remember.
8.
Yeah.
6.
6. No.
Are you guys just
1.
Okay.
Duh.
Now
It's
you're
3. How's it not 3?
4 factorial over 2 factorial, 2 factorial, which is equal to? Someone's already said the right answer, but I wasn't going to write it because they were throwing out random crap. If you can't do that,
6. It's 6.
6! Wonderful!
7.
I know you did!
Okay, wait.
Because 4 plus 2
I don't
equals
remember
6.
this now.
Oh, goodness.
Alright.
Alright, so that's the size of A. Now let's say the size of B is, or we'll say B is even, 3 of them
We only have
are the
1.
same gender.
So then 4 choose 1,
4 choose 3,
equals
which
4.
is 4.
It's what?
4.
It's not 4. There, I gave you a hint.
How
It's not
much?
1. There's 2 hints.
Okay. We have 4 kids and 3 of them have to be 1 gender. 4 choose 3 is the same as 4 choose 1.
Okay. So what's the answer? I feel like you were headed in the right direction.
4 factorial.
Oh, no. Huh?
It's not also 6, is it?
No, you just spin out random crap.
I am.
What are the... Okay, look. This was how many have exactly 2 boys and 2 girls.
Dude.
How many have exactly 1 boy and 3 girls?
4.
How many have exactly 1 girl and 3 boys?
4.
So how many have 1 of one gender and 3 of the other gender?
8.
8. There we go. So you could have thought about it as 4 choose 1 plus 4 choose 3.
Oh, then we have to add them. Right. Okay. See, that's what I was doing wrong.
So there's a 50% chance that you'll have 1
What?
of one type of gender and 3 of
That
the
is
other
so
type of gender.
weird.
So it's more probable that you'll have 3 and 1 than it is that you have 2 and 2.
Yeah.
Okay, but why don't you have to freaking plus it on A?
Plus what today? 4 choose 2 plus 4 choose 2. We already did 4 choose 2. I mean, we can flat out write this out. It's small enough.
Yeah.
It should have been.
We can have boy, 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 girl, boy, boy, girl, boy, 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 girl, girl. Is that right?
Boy, girl.
Boy, girl, boy, 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 girl, boy, girl,
Girl.
boy, girl, girl, boy, boy, girl, 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 and
Girl,
Let's take the bull by the horns. How many have 2 boys, 2 girls? 1, 2, 3, 4, 5, 6. Oh shoot, there were only 6. How many have 1 and 3? 1, 2, 3, 4, 5, 6, 7. And I missed one.
That's only right before.
8.
Oh, 8. There we go. Believe me now?
I did not believe you before.
I believe that you didn't believe me. So yeah, you have better odds of having 3 and 1 than 2 and 2. Very unintuitive. It's not my choice. The math's the one that decides. And then there's 2 ways of having all the same. Very unlikely. 1 in 8. It's not too bad. 1 in 8 families of 4 have all their kids the same gender.
So a family of 8. There's a chance of 1 of them.
What?
There's not a chance. That means it would have to.
Well, there's never have to in
Have
probability.
4 kids that are all the same.
If you have 8 people in a family,
Huh?
8 kids.
if you have 8 kids, 4 of them have to be the same gender.
No.
You can't have 5 girls
That's
and 2
what I'm
boys.
saying. Okay. Big one.
No, what you said is actually right. If you have 8 kids, 4 of them have to be the same gender.
No.
Just like if you have 4 kids, 2 of them
That's
have to be
all
the same
I'm
gender.
We're
Right.
talking about grandkids here. A person, they have 8 kids.
Okay.
And then those kids, this one has 4, this one has 4, this one has 4.
Oh, so one of them would, at least one.
And then one of them
Should.
would have to have 4.
Should.
Not would have to. Odds are.
Right, that's what I'm saying.
Yes.
And I would be back. Even though I literally, yeah, okay. An aunt that has all 4 boys, yeah, okay.
Oh, you think about real world scenarios?
Yeah.
Yeah. Yeah, so misunderstandings of probabilities come into all sorts of nonsense. One of the ones that drove me crazy when my wife was pregnant was all these stories about how you can tell what the gender of your kid is. A bunch of nonsense, but we'll go over it.
Yeah, it is.
Let's say that on average a woman has how many kids?
3.
4.
Wow, you guys are really high with your
2.
numbers. 2 is pretty good. I'll go 3. 4 is
Wait,
Well,
so
do
then
you,
like
do you know
2.5
where
or
we
2.3?
live?
well in America it's like 1.6. It's
Wow.
not even past
Just
2.
a half kid.
No.
So let's say it's 3. Let's say the average woman has 3 kids.
Just-
How many girls don't guess the gender of their babies?
I don't know.
0. Everyone guesses the gender of
Oh,
the
yeah,
baby.
yeah, duh.
Everyone guesses the
Right,
gender of the
right,
baby.
right.
Sure.
So, as far as doing statistics, yes. I mean, yeah, there's going to be offshoots of people that don't. But as a general rule, girls guess the gender of their babies. That means 1 in 8 girls are correct 100% of the time. Right?
What?
Odds are probably.
Odds are 1 in 8 girls predicted the gender of all their babies correctly. So if 800 girls have 3 babies, 100 of them are walking around at a 100% prediction rate. Pretty good, right? They must have some insight. And they must know how to predict.
So,
You're saying you just guessed.
They guessed. That's why there's only 1 in 8.
okay, how the freak does that work?
What are the odds of you guessing your first baby right?
50% chance.
1/2. What are the odds of you guessing 2 babies right in a row?
4.
What are the odds of you guessing 3 babies right in a row? Right? So, if you have 800
Is that a belly?
of them guessing, 100 of them got it right 100% of the time. and another 300.
Got it right.
Oh, sorry.
Almost got it right. Got one off.
No, because then how many of them are going to, another 100 got 2 of them, right?
No.
And then another 200 got at least 1 of them, right? And 400 of them
Didn't get it right.
didn't get it right.
Didn't
Right.
get any of them right.
No.
Only 100 got it.
That's a bunch of savages.
Sorry.
No, that's right.
400
No.
mispredicted the first baby.
What?
400 predicted the first baby right. I broke this down.
Right,
in the
okay,
back.
yeah, okay, see that.
Forget the picture.
Alright.
All that matters is that 100. So 100 out of 800 girls. So if you're in an area that has 800 girls, 100 of them are walking around.
If they have 3 kids.
If they have 3
That's
kids.
what you need to specify.
Oh yeah, that's what I specified.
Yeah.
So assuming that's the average.
That makes sense.
So then 100 out of 800 women predicted it. 100% of the time. 100% correct. So they must have some insight, right? Some secret to guessing that we don't have. That's the leap people make.
That is so damn funny.
When it's just completely random. It's why people think that they know how to gamble. It's so easy to get delusional gambling. Right? Just like it's easy to get delusional with this. If you guess 3 in a row, what are the odds of that? 1 in 8.
And even the average is lower, so if it was 2 kids, the odds go up.
The odds go up, right?
And then 200 out of them would have guessed it right.
Yeah, 200 out every 100 every 400 are out there thinking, I'm real good at this.
Wow.
I can predict it. And people just don't ever stop to think maybe that was just lucky. And so it leads to all sorts of
Yeah, but like,
nonsense.
you're also not a girl, so you can't really say this.
I can say this
Nuh-uh.
very easily. I'm pretty sure if you would go, all sorts of similar studies have been done with like homeopathics, for example. This one.
I mean, like, yeah, that's a logical reasoning, but like, I completely believe that they're women have connection and they don't. Like,
The gender of their baby.
yeah.
I highly,
They
highly,
have
highly
feelings.
doubt
They
that
have
the
feelings.
gender of the baby is producing any strong physiological side effect.
I believe that 100%.
Maybe it is. I don't know.
Well, sucks to be you, I guess.
You can do studies on it, see what women's prediction rates have actually been. And has it come out 50-50?
Oh, that'd be-
My bet is it has.
Agreeing.
But the part that adds on to it is, we don't have to talk about pregnancies necessarily, it's just gambling. So people who think that they get good at gambling, how many people go and talk about that time that they bet money and lost? So many. They talk about when they lost versus when they won?
Oh, you're saying that when they talk about
Yeah.
it? Not a lot.
We don't talk about that one.
They talk about their wins, not their losses, right? Oh, this one time, I was on such a roll, right?
Right.
And then this one time, I just got killed. I was an idiot, I lost $3 grand. They talk about that one time that they just killed it, right? And got that $3 grand. So you have the people who are winning are disproportionately talking relative to the people who are losing. And so it sounds like there's a lot more success out there than there really is. And the one that kills me is homeopathics. So I don't know if you understand how homeopathics work at all or the thinking behind it.
I want to just give it up
The idea is, well, the point is you're taking medicines that don't really have anything in them and getting better because of it.
Okay.
Okay? You're taking what are supposed to be such watered down medications that they actually, chances are, don't have any of what they're supposed to have in them. And they're supposed to somehow capture the essence of things. Special nonsense makes no sense. But how homeopathics got big is actually kind of interesting. Because homeopathics first got big, I don't know how many hundreds of years ago, but well into the past.
Wait, which ones
When-
are the homeopathics?
Well, the ones that do
Take
nothing.
it?
Yeah, you drink things that have nothing in them.
Wait,
So
so they
the
take
people
they
are-
take medicine, they water it down.
Kind of. This wasn't even medicine to begin with.
Okay.
No, they don't do it, the doctors give it to them.
Doctors don't do homeopathics.
Wait, what are you talking about?
Homeopathics, I thought that you would be more
What
familiar
is
with what this is.
homeopathic? Is it the medicine that they take, or
Yes.
is it the person?
Oh, no, it's the medicine that they
Okay.
take. Oh, sorry. Yeah, so it's something that you actually consume.
Are you talking, I feel like.
Like a liquid that you
You're
consume.
talking about like essential oils and herbs.
Essential oils are kind of there. Herbs, no, not there. But it could have been made with herbs, supposedly.
Okay.
But it comes down to this watered down nonsense that it will do nothing for you. But the reason it got big is because when they first came about, or at some time after they came about, you were actually far better off to take homeopathics than to go and get actual medical procedures done.
Why?
Because chances are medical procedures at the time would hurt you more than they'd help you. So people who would do homeopathics instead of traditional medicine at the time
More healthier.
were healthier. And there was a better success rate doing that. So for example, there came a point in time where they thought their theory about fluids in you was so weird, but somehow you had to keep it balanced, and like leaching was a thing, drain your blood. The idea was get the bad blood out, your body would produce new healthy blood. Something to that effect.
Right.
So leaching was a common thing where you just like bleed the disease out of you, which makes no sense. And we know that now. So it turns out drinking water that does nothing to you was far better off than going and bleeding yourself. And so people getting cured by the physicians were dying at a higher rate than people who were going to the homeopathics. Turns out the person who was doing nothing had the same success rate as those going to the homeopathics, but you get better and you want to instantly assign it to something. Right? I'm sure you've heard about the placebo and the nocebo effect. Yeah? No? What's placebo effect?
It's the idea that you think it's getting you better, so you get better, and then you say, oh, that got me better.
You think it's getting you better. It actually comes back around though. So how it typically happens is you do something, it gets better, you think that's what made you better, and so from there on out, you doing it actually does help. It's the craziest thing.
It's
And then the-
totally mindset. If
I
you-
don't know
if
everything's
you
attributed to.
If you're getting better, you're getting better. If you are, you know,
It helps. Is
if you're
what the
freaking drinking
placebo.
water that you think is making you better, it's making you better.
Right, it's better that you think it helps than knowing that it doesn't do anything for you. Because then it actually helps.
It
Right.
does.
Right.
It's kind of weird.
That's
And then the nocebo is the same idea. An example of the nocebo effect, a common example is, I look at a computer screen for a long time, I start getting a headache, I will go away from the computer screen, get up, start walking around, and my headache goes away. Conclusion, computer screens give you headaches. Well now, computer screens are more likely to give you a headache because you believe that they will.
Oh, that's so cool. I love
So it goes the other way as well. So when it has a negative effect, it's called a nocebo effect, and when it has a positive effect, it's called a placebo effect. But yeah, real fascinating stuff. So that comes into play. So I would guess that people taking the homeopathics actually did have a better success rate than people not taking them, and a higher success rate than people taking nothing, simply because
Not a thinking about it.
yeah, placebo effect. It's like a weird phenomenon.
That's awesome.
It is. It's fascinating.
I
Huh?
believe it.
It's well documented. Every time we do medical studies, we have to have placebos. And yeah, so it's a well documented phenomenon. Absolutely crazy, but it works. Okay. The birthday problem.
Reading over the proposition here.
What's the proposition? Oh, yeah, proposition 31.7.
Yeah. And
The AUV events, huh?
And 31.8.
Oh. Oh yeah, we should probably go over that one since we used that already. You guys didn't do good on it. 31.7, the A and B events in sample space, and the probability of A plus B is the probability of the union of A and B plus the intersection of A and B. Oh, we kind of already know that. Okay.
So what's our homework? Just 30?
Yeah, maybe we'll just pick it up there next time since we have 2 to do next time, right? Do you have the syllabus in front of you? So that was section 30, right?
Yeah. and
Wow,
we
I
have 30.
really started easy. And then 31 and 32.
Yeah,
33,
like the
34.
rest of it is super easy.
Okay. Yeah, so we'll call it right there. Next time we'll finish 31, 32, so you can start your homework for 30 in case maybe the homework problem is just hard and you'll probably need my help with it.
Okay.
So that was a
Only
quick class.
5.
Yeah. So feel free to go on break after that. We'll just do homework. I'll be here to answer questions.